In this lesson, we start laying the foundation of our software application. And I'll start by describing two design patterns often used in bare metal embedded software that are the keys to this foundation. By design pattern, I mean a way of doing things that is copied or reused by others to solve a similar problem. The term is not super precise. It usually does not mean direct reuse of code like in a library, but more the general way a problem was solved. Now the first pattern is the super loop. This is simple but widely used. The problem it solves is sharing the CPU between different parts of your application. I used a super loop on my very first project over 35 years ago, but I didn't know it was called a super loop. I think I just called it the main loop. Frankly, I think the term super loop is a bit of an exaggeration. Maybe it is something you say to impress your friends and family when they ask you what you do at work. So you say, yeah, I've been working on the super loop. Anyhow, the second pattern I want to talk about is modules. Now, the term module is so generic, it can mean many things. In this class, it is something simple and obvious and less commonly used. Its purpose is to provide some structure to your software and allow it to be broken down into pieces, divide and conquer, as we say. Also, sometimes modules can be reused between projects. This might be for things like a command console or timers that are needed in many embedded applications. In future lessons, I will introduce a set of generic or infrastructure modules I have developed as examples for this class. They are similar to what I have used in my career in one form or another. If I were developing a bare metal application today, I would use these modules. They are not rocket science, but they are simple and they get the job done. Now for the super loop. A super loop design is simple. Let's start on the left side of this slide. So your MCU powers up. First, you do some lower level initializations such as clocks, memories, and other hardware. The stuff we just looked at in a previous lesson. Then you do module initialization. You initialize all the modules and then you start all the modules. And then you go into an infinite loop where you repeatedly run the modules. Now here is a trivial example of what modules might do in this loop. There might be a module that reads inputs. There might be a module that performs application logic, and then another one that writes outputs. And that's all there is to it. What makes it so super? I don't know. It is the top level loop, so I guess it is above any other loop in the software. On the right side, we see what the code might look like. Each of these boxes might be a different source file, although that really isn't important. The first box represents the reset handler that gets called at PowerUp. I show this as being C code, even though the reset handler we looked at in a previous lesson was written in assembly code. Anyhow, it does some low-level initialization and then calls main. Now, in main, we assume there are two modules named A and B. And we assume there are functions to initialize, start, and run these modules with obvious names, as you'll see. So the first thing main does is call all of the init functions for the modules. It then calls all of the start functions for the modules. Then it enters the infinite loop and continuously calls the run function for the modules. Now, one thing about these run functions, it is common that these functions are written to never block. By block, I mean wait for some event or condition. In many systems, it is essential that they never block. Instead of waiting, they should just check for the condition or event every time they are called. If none of the run functions block, then the super loop will be super fast and the system will be responsive. Now, below the main file, I show some files with interrupt handlers in them. I label them as optional. Now, here's the deal. As you know, interrupts allow the MCU to respond very quickly to events such as a timer expiring, or a character received on a UART for a serial line, or an A to D conversion completing. In some cases, you can handle these events in the run functions, called from the super loop. The functions will check the hardware fast enough. This is known as polling, and in this case you don't need the interrupt functions. That means less code, and less code usually means a simpler design and fewer bugs. This is especially the case with interrupt handler code, which tends to be tricky. However, in other cases, the super loop will not run fast enough and data or events will be lost. In this case, use of the interrupts is the solution because interrupts get called immediately when needed. We'll see an example of this in a later lesson. Now, it might only take the MCU a short time, say 50 microseconds, to run through the super loop. And you might ask, isn't it a waste to run that fast if running through the loop maybe just once every millisecond would be fast enough? That's a good question. Now, with some MCUs, there is not much you can do about it. You could try to put in a delay at the start of the super loop, but the MCU will just run in a loop waiting for that delay to end. So you might as well just run the super loop. However, other MCUs have sleep modes where much of the hardware stops running and power usage is greatly reduced. So we might be able to save a lot of energy by sleeping when we can. The question is, how do you sleep just the right amount of time? Well, the MCUs have an answer for that, which I'll show here. The key is this first line of the super loop. It is calling wait for interrupt. Now, I made up this function name, but what it would do is use a feature of the MCU that causes the processor to go into a sleep mode until any interrupt occurs. Then the processor starts running again. For ARM processors, there is a wait for interrupt machine language instruction that does exactly this. Now look at this systic interrupt handler function here at the bottom of the slide. The comment implies that the system tick interrupt is every 1 millisecond. So if we are in this wait for interrupt at the top of the super loop, we will wake up at least once per millisecond. We might wake up more often if there are other interrupts, but that's okay. It just means we'll run a little bit more than once per millisecond. So in this implementation, the CPU might be able to save a lot of power by sleeping, even if only 1 millisecond at a time. So that's it for super loops. I will finish by adding that you might see various tweaks for super loops. For example, if the number of modules in the super loop is very large, and there is a module that is very time critical, then that module could be called multiple times within the super loop. Another tweak is that the system could have different modes of operation, and based on the mode of operation, different run functions would be called in the super loop. Regardless of these tweaks, the basic idea of the super loop stays the same. Now let's talk about modules. When we looked at the super loop, we saw functions like a_init, a_start, and a_run. This was giving a little preview of the basic module concept. Now let's look at it in more detail. One of the earliest and most basic ideas in software design is to divide and conquer. It tends to make the code more flexible and easy to understand and makes it easier to split work between developers. The module concept is used all over, with different styles based on the environment and preferences of developers. In this course, I will use a module style that I like for bare metal embedded. You might not like things about my style and do it differently. The important thing is to define a consistent style. Developers like consistency. One of the things the module concept does is provides a pattern for things like naming conventions and a core set of API functions. Maybe this isn't such a big deal, but it is nice when creating a new module not to have to spend time thinking about this kind of stuff. And it gives some consistency to the code. As I said, developers like consistency. Of course, the super loop primarily consists of using module APIs. With consistent naming and APIs, the super loop also becomes nicer looking code, and developers like nice looking code. As a final point, the module pattern does not have to be rigid, at least in my opinion. If a particular module needs to deviate a little from the standard API pattern, for example, you can do it. Or if you want, you can generalize the module API pattern to accommodate the deviation. It's up to you, and I suggest you don't overthink it. Now we'll start to get into the module style for this course. Before we get into the nitty-gritty, I want to talk about a few concepts that are used. One is the module type in terms of the number of instances. For those of you familiar with object-oriented programming, an instance is like an object. Now a module can be a singleton. This is a fancy computer science word meaning there can only be one instance of such a module. An example might be a logging module. One is all you need. Generally, singleton modules are a little bit easier to implement and use. There are also multi-instance modules. An example might be a serial port module, where you have one module instance for each physical serial port. Then there is a case I call a hybrid. In this case, there is only one module instance, but it manages multiple resources. An example could be a software timer module. There is only one software timer module, but it manages multiple timers. We will actually see such a timer module later in this course. Next, I want to talk about the module lifecycle stages. By lifecycle stages, I mean how a module gets created and moves to the running state. This may be more clear when we look at the API in a minute. The first stage of the lifecycle is module initialization. During initialization, memory is allocated as needed. Now, in many cases, the memory will already be allocated at compile time through static or global variables. However, memory allocation could involve use of the heap if you are using the heap on your project, and that is another topic. Also, during module initialization, the configuration is passed in by the user and stored in the module instance as needed. Now, when a module is being initialized, it should generally not try to access other modules, since they might not yet have been initialized. But there might be exceptions. For example, a module might be designed such that it doesn't need explicit initialization, so it can always be accessed. Or you might initialize the modules in a specific order, and this will be done so that modules initialized later can access modules initialized earlier. In any case, by the end of the initialization phase, modules should be ready for access by other modules through the API. The next stage of the lifecycle is module startup. The main purpose of this stage is to allow modules to access other modules as needed before entering the run stage. Keep in mind that all modules will have been initialized before any are started. And then the final stage of the lifecycle is module running. This, of course, is the major part of the module's life. The super loop will be repeatedly calling to the run functions for the various modules. Some systems might have a module shutdown or termination stage in the life cycle, but in many embedded systems there is no formal shutdown or termination, so I didn't include such a stage, but it could easily be added. Lastly, I want to just re-emphasize the point that all modules are first initialized, then all are started, and finally all are run in the super loop as needed. Now we get into the details of the module style. First, every module has a short name, 3, 4, 5 characters or so. For example, log or TMR for timer. And this name is used throughout the API for the module. For this lesson, I will use the placeholder XXX to represent that name. There will be at least two files, a header file named xxx.h and an implementation file with the name xxx.c. The header file contains the public API and nothing else. There could be more files in these two, but most of the modules I have worked on were pretty small, and two was enough. In general, modules might require configuration parameters. If so, the parameters are put into a struct like this. Notice the struct starts with XXX. Examples of parameters are timeout values and hardware IDs. Now for the core API. We have 4 functions in the core API. As you will see, they all start with the module name. The first API is used to get the default configuration data for a module, if configuration is required. This function frees the module user from having to know the configuration default parameters and fill them in. It's especially handy if there are many parameters and you only want to set one. You just create a structure, call this function to get the defaults, it will fill them in, and then you modify what you need before doing the module initialization. This next function initializes the module. Note we pass in the configuration. As I previously mentioned, modules generally should not access other modules during initialization, with some exceptions. Continuing on with the core API, the next function is used to start the module. In this stage, modules can access each other, and that is the main difference between the initialization stage and the start stage. Finally, the run function is the one that is repeatedly called from within the super loop to do the work of the module. Now, most modules will have additional APIs that are specific to that module, and this could include functions, structs, enums, typedefs, hash defines, and so forth. For example, it could be a function to get a analog input value, or send a message over a serial link, or start a timer. Now, all of these public functions or symbols should start with the module name for consistency and to avoid name clashes. So a few final things about style. Generally, I follow the Linux kernel coding style. Here you see a link to it. The Linux kernel is perhaps the most important piece of C code in the world today. My feeling is that if a coding style is good enough for the Linux kernel, it's good enough for me. But there are plenty of people who don't like it. And I do have one major problem with it. It says to use 8 space tabs to indent code. While I used to think that tabs are the right way, I switched to using spaces about 5 to 10 years ago. This was when I started writing Python. And 8 spaces is just too much in my view. Finally, you will eventually encounter the question of whether modules should implement all core API functions, even if some are not needed, just for consistency. For example, what if there is nothing to do in the start function? Should I just create a dummy function? Well, there are arguments either way, and in my view, it's not a big deal. However, in this course, I only implement what is needed. This means that main and the super loop have to be written with knowledge of which APIs each module implements, and perhaps that's the biggest downside. One final note about modules. Modules can be a mechanism for hardware abstraction. Here's my thinking. Formal standalone hells can be difficult design. This is especially the case if the hell is supposed to support hardware that is vastly different, like MCUs from different manufacturers with different architectures. Now, it might seem it shouldn't be that hard until you try it. You find that the devil is in the details. Modules are an alternative to hells to support multiple hardware platforms. And here is the key point. With HAL, you are providing an abstraction of a hardware device. With a module, you are providing an abstraction of a service. So the focus is supporting the module's service-oriented API and nothing more. You don't need to worry about all the possible uses of the hardware, just what is needed for the service API. Also, modules are part of the execution environment of the system. That means the superloop. Now, this idea might or might not be useful to you, but it is something to consider when faced with the prospect of supporting multiple hardware platforms. You could use the modules as the way for that kind of support. So that is all for Superloop and modules. The rest of this course is all about these topics with lots of examples. Thanks again for watching.